So we move into Chapter 2, and Chapter 2 is all about conduction. Do you know there, if you go to graduate school, a lot of universities, mechanical engineering program will have a whole class for a whole semester. It'll just be conduction heat transfer. Very mathematical, very rigorous. You can spend a whole semester. We don't. Okay, we're just going to spend a little section here, this chapter. It's a little on the mathematically intense side. But that's okay. Let's see what we got and let's get through it. So first of all, we'll have the conduction rate equation. That's simply Fourier's law. Fourier's law in 3D. And then we'll talk about the property that's important, the thermal conductivity. We already did it. We'll spend a little more time talking about that property. We'll talk about the heat diffusion equation, which is a conservation of energy statement. And how can the energy flow in a material? By diffusion. And maybe it's flowing into a location and the temperature would go up, 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 so you could have the change in temperature with time. And that'll be in the heat diffusion equation, just like we had in thermodynamics, the energy, first law of thermodynamics. And then also in the heat diffusion equation, we'll have this volumetric heat source. It's like a source of heat. It's not like energy is being manufactured. It's just in our counting system. We're keeping track of this type of energy, the thermal energy, the internal energy, and it can be transferred by heat transfer. All right, and then we have boundary conditions. With the nice differential equation, mathematically we can solve. You could solve for things like what's the temperature distribution in this material. Once you know the temperature distribution, what's the heat flux? How is the heat flowing through this material? That's the whole chapter. Should we stop now or continue? A little more detail, Professor. Well, okay, so Fourier's law, we've been introduced to it, and it's basically a rate equation that describes the rate at which heat is being conducted. So it's the conduction rate equation. What does it look like in one-dimensional? It says Q sub x equal to minus K. Let's put it in a flux term, so I'll leave the area off. I'll divide through by the area. dt dx. How about if I go into 3D? And maybe the 3D rectilinear, maybe the 3D Cartesian, or cylindrical or spherical. Well, in general, you would write it like this. You would write Q double prime, and it's a vector quantity, equal to minus K. What? T? What is this symbol? Upside down difference symbol? Gradient. Hey, yeah, you remember the gradient. So the gradient of the temperature field. In the gradient operator in our favorite coordinate system, the Cartesian or rectilinear coordinate system is it's this partial of give me something with respect to x in the I plus the partial of give me something with respect to y in the j and the partial of give me something with respect to z in the k. So you have to feed the gradient operator something. So, it's whatever you feed it. In this case, we're going to feed it temperature. Temperature, temperature, temperature. And so you could see it's going to return back an I, J, K at every location. It's going to return back a vector. At every location, that means it's a vector field. Okay, so that's the gradient. All right, very similar operation in 1D for the cylindrical and spherical coordinates. But we're going to spend most of our time with this rectilinear or Cartesian coordinate system. So right away, you have the difference. You have temperature at location X, Y, and Z. That means at any location, I should be able to, if I knew the temperature distribution, get a value for the temperature. So the temperature is going to be either a scalar field or a vector field. It's a scalar field. It's a scalar field. But then you take the gradient of the temperature, what we just talked about. That now gives you back a vector field. At every location in the domain of interest, I get a little vector. That vector has both direction and magnitude. And it's telling me in that direction what is the rate of change of temperature if I move in that direction. take a look. What is the units on this one? Degrees C. Units, degrees C per meter. That would be like, what's the temperature change as I move spatially? Okay. Then heat flux. Well, how did we get heat flux? You just take the gradient of the temperature, multiply by the property of the material, and throw a negative sign because it's always flowing from hot to cold, not cold to hot. So the gradient is positive in a direction where it's increasing, like the slope is going up. That would be a positive gradient. Well, the heat flow is an opposite. The temperature is the temperature gradient, you multiply by a negative sign to get the direction of the heat flux. A lot of times, maybe you'll see this in a textbook. Maybe I'll do that too. They'll say, oh, put a little vector symbol on top of that gradient and a little vector symbol on top of that Q to emphasize that, hey, we're talking vector quantities now. All right. Hey, what are the SI units for the heat flux? This one right here. Watts per meter squared. That's right. Yeah. All right. We'll talk a little bit about fields, the temperature field. A lot of times you'll have thermal contours. They'll color code. Maybe the blue is cold, the red is hot. And then maybe you come in here and you would be able to sketch a line of constant temperature. That would be an isotherm. That would be a different isotherm. Maybe this is a different isotherm. Maybe this isotherm kind of goes like that, you know. Okay, in our domain. So if you wanted to visually represent the temperature field, you use color graphics like this, and maybe you draw lines in 2D or 3D. Now, how about the heat flux? Well, it would be represented by a vector field. Every location, instead of a value, you have a vector. So at this location, typically we draw it where we can on an isotherm. At this location right here, it would be a vector in that direction, meaning it's moving from hot to cold, and the length of that vector indicates the rate at which it's flowing, some magnitude of flux. Here, maybe at this location it's like this, maybe at this location like that. It's always perpendicular to the local isotherm. So at this location it'd be like that, perpendicular to the isotherm. That would be the heat flux. All right. And so any place out, you could just pick, numerically you should be able to get the flux at any location if you have the temperature at all locations. All right. So we had this quick, what is the conduction rate equation? If you had the clickers working, we'd pick one of those. But without the clickers, which one is it? Fourier's law. Yeah, Fourier's law. So property of importance is a thermal conductivity for conduction. The symbol was K, units of watts per meter degree C. We were introduced to it last time. It's simply a property of the material. That property can be temperature dependent, or it can be pretty constant and not temperature dependent. It can be spatially dependent. Yes, it can be even directionally dependent. But in a lot of cases, it's just a simple number. We neglect spatial dependence. We neglect temperature dependence. All right. It's a measure of how readily heat passes through the material. We said if it was low, that's a good insulator. If it was high, if the thermal conductivity magnitude of it was high, it's a good conductor. And you go back and look at the 1D, q sub x double prime equal to minus k dt dx. And you say, well, take that equation, rewrite k is some q double prime divided by minus dt dx, is it not? So you could say, well, it's the magnitude of the heat flux for a given temperature gradient. And so one way of thinking of it is, what is the heat flux per 1 degree C per meter? A standard sort of gradient. That's one way of trying to give physical interpretation of K. Or you just say, hey, K is a property. If it's low, it's an insulator. If it's high, it's a good conductor. Well, 99.99% of this class meaning almost never is it the other case. But 99.9% of the class we deal with what we call isotropic materials. Isotropic means the property has the same value measured in all directions. It does not change because of the direction at a location. Okay. Well, what's the opposite of that? If you have an isotropy, or if you have anisotropic material, that would mean that you have the property of interest changes depending on the direction at that location. And for a wood, which is a natural material, you can think about how the grains affect the property. You could have that true for the solid strength of the material, here stronger in particular directions. It's true also for how it conducts heat. Another example that's not a physical example would be a composite material. You know, they lay fibers and composites and resins. A lot of it's for strength, but then also maybe it changes in its conducting heat a little better in one direction than the other. So this is the reality. Some materials are composites, or they have directionally dependent property like thermal conductivity, but the vast majority, and if not all of this class, is isotropic. Let's review again something about gases, liquids, solids. So if you just sort of had decay, the thermal conductivity on the x-axis, what tends to have high values? Metals. Yeah, solids, metals. Non-metallic solids, a little less. Then you have liquids, and then you have gases. So the gases have the lowest thermal conductivity. Sometimes a plot like this, it's helpful if you kind of say, well, what's the lower bound and upper bound, right? You know, and it would be, somebody says, oh, I have this gas, and the thermal conductivity is coming in at 0.001 watt per meter degree C. I'd probably tell them, go look for an error somewhere, because this seems to be outside of the range that seems plausible for your gas. Likewise, somebody comes in, I got a new material, I built it in the lab, constructed it, it's new, and it's 10,000 watts per meter degree C. I'm sure that experimentally somebody's gotten it, but it's pretty exotic and probably very limited. Maybe it has a very unique characteristic and dimension or property, brittle and other things. But anyway, it's way outside the range of that would be normal. Hey, what was the value of copper? About 400. Cut it in half, around 200, you've got aluminum. If you want to build stuff out of gold and silver, well, then it'll be higher. But gold and silver are pretty expensive. We don't do that for thermal properties often. But we do pick things to be copper and aluminum often in engineering applications because of their high conductivity. What is, look at the value of air. We work with air. We're breathing air. It's all around us. If you can hold air stationary, you keep it stagnant, which is hard to do, because once it's a little hotter over here and colder over there and we have gravity, it likes to move. But if you can keep it with no bulk motion, look at the thermal conductivity of just stagnant air. It's really low. It's pretty low. Like 0.02, 0.025, somewhere in there is the value room temperature. What about water? Somebody says, I need the thermal conductivity of water. Your life now depends on it. You're going to say, I need a textbook, I need my Google, internet search capability. Nope, none of that. You're stranded. Give me a value of K for water. What are you going to tell them? 1. 1. There you go. They're just about 1. It's a little less, but there you go. It's temperature dependent, of course. So anyway, that gives you kind of a range. When I forget, I was in doctoral qualifying exam, and I was answering all their questions nicely, and then all of a sudden they say, we'll get them on this one. And they say, give me a value of blah, blah, blah. And it was like, I didn't know it. It was like, what's the value of the thermal conductivity of stainless steel? I don't recall. I don't remember it. So anyway, they always find a way to put you down or to not humiliate you, just take the air out of your head. Keep the size of your head small. Anyway, these are good numbers if you can, if this is an area where you're really interested in working for a long time, that you might want to start paying attention to the values. Otherwise, just get through this class and then flush it later, right? Yeah, there you go, huh? So silver is kind of on the high end, gold's on the high end, then you got other metals. If you got alloys, aluminum's up there. This is a plot just showing you, to build a good insulator, just a recipe to build a good insulator, get air to be stationary. That's it. So what do you think the spun fiberglass is that you put in home attics? Is the fiberglass? That's glass. That's actually a pretty good higher K than the air. Why are you putting fiberglass in the air? It seems like that mixture is going to be overall a higher thermal conductivity. Well, it's holding air stationary. That's what it is. If you have a foam, like a styrofoam cup, there's little air pocket bubbles in it with a little matrix material to connect between them, but to hold the air bubbles in their locations makes a very good insulation. All right, and then liquids, and you can see that you could have liquid mercury. We don't see that too often in applications, but maybe there's an engineering application that you may run into where it's out there. Oils, we just talked about water, talked about solids like ice, different plastics are pretty low, but there's just range of values for thermal conductivity. Now, one of the things is if you have a good electrical conductor, then it gives you high thermal conductivity. Kind of like the same mechanism that allows electricity to move through the material, same mechanism that allows heat to move through the material. So there's a trend. So if you really want a good electrical conductor that is a poor thermal conductor, a good insulator, well, good luck, right? Yeah. So, all right. It just means you're going to be looking for an exotic material that's out of the norm. Let's take a look here on this plot. It's a function of temperature, and we have thermal conductivity. It's a very low value of thermal conductivity, then it's a little higher, then higher. But let's try and point out things like what's water? Water's a liquid. How about ethylene glycol? That's a liquid. How about engine oil? A liquid. How about hydrogen? Gas, H2, likes to float around. Helium, helium, gas. Air, gas. Steam, it's a vapor, gas. Maybe not an ideal gas, but it's in a gaseous form. And then ammonia vapor, again, maybe it's not an ideal gas, but it would be a gas. So CO2, carbon dioxide. As a general trend, liquids have higher thermal conductivity than gases. But there's a few unique gases that really have high K. What are the two that have high thermal conductivity? Hydrogen and helium. What do we know about the molar mass of hydrogen and molar mass of helium? Really, really low. From memory, what's the molar mass of hydrogen? 2. 2 is low. 2 kilograms per kilomole, 2 grams per mole, whatever you want to give it per units. And then helium, molar mass of 4. And every now and then you'll see an engineering application where they want to use the hydrogen because of the low thermal conductivity, or the helium for the low thermal conductivity. For the high thermal conductivity that it has. Okay? All right. But in general, gases have low. Again, we talked about this a little bit in the first lecture. Temperature dependent, some of them, they're not maybe as strongly temperature dependent. Here's temperature going this way. This is the thermal conductivity. Here's aluminum, here's brass, here's platinum. You just have to look at your material and look at your range of temperature that you're working in and think, is it pretty constant? Is it pretty flat? Or is it a great slope and a great change? So we talked about Fourier's law. We talked about the gradient operator. We talked about the heat flux. We talked about the thermal conductivity. Now let's take a look at the heat diffusion equation. And here is a representation of that equation. You look at it, and it's the del dot. Back to engineering analysis, talking about vector differential calculus. That's the divergence, and then they have K grad T, that's the gradient, that looks like the heat flux without the minus sign. And then you have Q dot, that's a heat source, a source of heat. Where would that come from? Electrical resistive heating or some sort of chemical release of heat that would be modeled in your heat equation, or even a nuclear type of, not a chemical, but a nuclear fissioning release of heat. And then over here, what do we have? Well, that looks like a time rate of change of temperature. Hey, something's going up. It could be accumulating internal energy, and it would be represented by a higher temperature going up with time. So this is an accumulation depletion term. Okay, it basically is a conservation of energy. Not all forms of energy, but just a particular form of energy, the internal energy. Internal energy transfer by conduction, showing up in the energy equation by the electrical resistive heating and other things, and then the accumulation of internal energy. It's used to calculate the temperature field, the temperature at all locations. That's why we want this equation. It is a PDE, partial differential equation. And to solve it, not only do you need the equation, you need appropriate conditions, boundary, as well as possibly initial conditions. And you have the vast majority of the time we work in rectilinear or Cartesian coordinates, but we should be able to work in cylindrical every now and then, but only really 1D radial. And for this class, 1D radial for the spherical. Believe me, 2D, 3D spherical is beyond the scope of this class. We don't want to do it. It's just 1D radial in the spherical and 1D radial in the cylindrical. Okay. So we're going to come in with a new property. If this K is constant, it can come outside. And then often people will write this equation as del squared T plus Q dot divided by K equal to rho C over K, the partial of T with respect to time. And this property right there is often called alpha. It's K over rho C, or so it would be written as 1 over alpha, the partial of T with respect to time. Okay, so alpha is a new property, but it's just K, the thermal conductivity, divided by the mass density and the specific heat. So it's just another grouping of properties, because K is a property, rho is a property, C is a property. It's a little harder to interpret. What is the meaning of alpha? Well, it's a measure of how readily heat passes through the material and heats it up. Heats the material up. So some materials can heat up rapidly as well as cool down rapidly. Some materials, they're more like a freight train. They're going to heat up very slowly, but once they're hot, they're not going to cool down very fast either. A lot of inertia. Okay. So it's a comparison of the conductivity, the numerator, to the volumetric heat capacity. This rho C is a volumetric heat capacity. Other than that, it's just a property. Start to use it to see how it's used, look at the values of it, and as you do, you often struggle with, what does this property mean? Well, here you go. But for this class, it's been introduced. All right, I've taught this class a few times. I, like a lot of faculty, love derivations of equations. I could start early and just derive the equation, but then after a number of times teaching it, the students would say, less derivation, more application. And once I see the value of the equation, maybe I'll go back and review the derivation of the equation if I have some interest in it, etc. So what I'm going to do in 2 slides is derive the heat diffusion equation. It's an energy balance statement. That's how you derive this equation. So we start off, and we have our coordinate system, and we have the interest, the volume of interest is out there, and we select a portion of it. And we identify that portion by a control volume. And that control volume has an interior, like you would expect, and a well-defined boundary that encloses that interior. Okay. So you think, what is an energy balance, an internal energy balance statement for that control volume? It's not a total energy, just internal energy. So you say the accumulation going up or down of the internal energy in that system, in that control volume, will be changed by the conductive heat transfer. If I have more conductive heat transfer from across the boundary into it, then it's going to go up. But if the net conduction is negative in, then it's out. It's going to make it cooler with time. As well as we could have some generation. We talked about that already. Think of electric resistive heating showing up. So we work with the accumulation. We say, what's the internal energy? Mass, specific heat, temperature, minus a reference temperature. That's how you would measure it. So if it's hotter, has more internal energy. If it's colder, lower internal energy. So you say, I want it for the entire volume. Go ahead and integrate over the entire volume. And then you say, I want to take the time derivative of this term. Well, the time derivative, don't change the volume location with respect to time. So the time derivative comes inside the integration. And rho and c, can you see? I treat those as constants, not a function of time. And so it really hits not on the reference temperature. That's not changing with time. It just hits on the temperature right here. So this is my accumulation term. Now let's work on the conduction term. When you work on the conduction term, you have to think about every point on the surface. And what we talk about is getting the value of the heat flux. That's the direction of the conductive heat flux. And we have to know the orientation of the surface. That orientation of the surface is given by an outward directed unit normal vector. Why isn't it inward directed? Or is it inward directed for 50% of the textbooks and outward directed for 50%? I am happy to report that I've never seen an inward directed unit, normal vector for an area. Every textbook I've seen, it's always outward, which is nice. So that's what that N is. So if it's outward directed, and I have the heat flux is flowing out of the control volume, I do a dot product of these two, multiplied by the little magnitude of the area right there, and now I know the rate at which it's flowing out. I then do the summation over all the chunks of area, and now I have the net transfer out. Professor, is this going to work if the outward directed is in that direction and the red flux is actually in the opposite? It's flowing. Sure. It'll be a negative out. It'll be an in, actually. The math will work. So this is an area integral. What you do is you replace the heat flux by somebody's law. I forgot the name of that guy's law. Fourier's law. Fourier's law. Makes it a little more difficult, but hey, there it is. Okay. What is that little bullet right there in the middle? What's that for? Dot product. We know how to take two vectors and dot them. Yeah. All right. So if you want the net in, just switch the sign instead of a net out. The next term is a volumetric generation term. The book uses Q dot. I would have preferred the book to use the different symbol. I would have preferred the book to put Q triple prime. But the book didn't. And I want to be consistent with the book. Otherwise, students get confused. His notes differ from the book. I'm so confused. So let's just say it's Q dot. That's watts per cubic meter. Now, I do add a little subscript right here to try and say this is a heat source. The book doesn't put source on it. It's just Q dot. All right, watts per cubic meter. It's a volumetric heat source. So that's pretty simple. You just sum up over the volume, and now you have the total heat source in watts into the energy balance statement. That's the last term. We had a volume integral, another volume integral. We have this little area integral. Aren't you glad you took EA2? It's not Green's theorem. It's the divergence theorem. that's needed. And so the divergence theorem says that when I have this heat flux dotted with the outward directed normal vector over the area, that I could just say that's equal to the divergence of that same flux, now not integrated over the area, but integrated over the volume. You can go back and look. Every calculus book has a divergence theorem. They may call it Gauss's divergence theorem. Maybe you remember it that way, but it's different than the Green's. All right. So now I have a volume, volume, volume. We put them all together under one umbrella, one big integration. You said, you know what? This was arbitrary. The volume was really arbitrary to begin with. Somebody made it look like a peanut. Somebody made it look like a sphere. Somebody made it look like a funny shape. But I can push that volume down, down, down to a little point. You know what? It doesn't take much to conclude that the integrand must be equal to 0 at every point if the integral is equal to 0 for any arbitrary volume. So then, that's it. That's the equation. That's the heat equation. So if K can come outside, then we have del dot grad T. That's the del squared. That's the Laplacian, your old friend. If you want, you can divide through by K, and you see your thermal diffusivity show up. So there's different forms for the heat diffusion equation, but this is here in the red box. 2 slides. Was it helpful? I could spend them 2 weeks on this. No, we don't want to do that. Move on, Professor. So what you do is you expand out the del squared term in the rectilinear coordinate system. You expand out the del squared term in the cylindrical, and you expand it out in the spherical. The other terms, Q dot and this accumulation depletion term, are pretty straightforward. Now again, I said that we are only going to do 1D radial and 1D radial. So if you're only going to do 1D radial, it's only a function of R, not a function of phi or z. So those terms go away. Simplifies it. Likewise, in spherical, it's only temperature is only a function of R, not a function of theta or phi. Those terms drop out. So it's a kind of interesting. You have these long, impressive equations, and so you can show them to your friends and say, oh, these are types of equations we have to handle in heat transfer. And their jaw will drop. But you won't tell them that this part is never dealt with. You know, yeah. Okay. Likewise, if it's 1D up here, typically it's in the X, and so it makes it a lot simpler. So the heat diffusion equation, the equation we just shown, is a statement of, would you call it first law to be its closest example, or the second law, or Fourier's law, or Newton's law, or Stefan-Boltzmann law? There you go. It's really just a conservation of energy, but a particular type of energy. It's that heat energy or internal energy. Not all forms of energy. Boundary conditions. Once you have the PDE, you need boundary conditions. It's like, oh, the temperature at X equal to L is equal to a specified value, TS. Or the heat flux, which is Q double prime, at X equal to L is equal to, I don't know, specified value, QS. And then you say, well, isn't this related to Fourier's law? Sure. So it's minus K dt dx at X equal to L. That's equal to QS. You have to mathematically get the right boundary conditions to then solve your differential equation to get the temperature distribution. Let's solve a problem. So we have a plane wall that has thickness 2L. So if it has thickness 2L, that's kind of an indication that the center line is at X equal to 0. And if you go over here to this one surface, it's thickness L going halfway across. And over here, it's negative L. So the X coordinate system starts in the middle, center line, and goes. So the slab is X goes from negative L to positive L. Okay. This is common right here. Okay. There is a heat generation in the wall, Q dot, make it a little challenging. And both wall surfaces are maintained at a temperature Ts. Let's use the y direction to help us sketch the temperature profile. So we'll sketch temperature going up. Maybe we'll put it here and here to indicate Ts and Ts. Because there's heat generation, do you think the temperature inside the wall is going to be higher? Yeah. And so you think about it for a minute, you think, well, it can't be flat. Maybe it's peaked like a hat. No, it's probably going to be something like this. And probably from symmetry, I could cut it in half straight down the x equal to 0 plane and flip it over, and wouldn't it be symmetrical? Yeah, it looks like it'd be symmetrical. So a little, go back to math, but what do you think about this slope of the temperature profile at x equal to 0? 0. So right away, you could say that we have our differential equation and our boundary conditions. The differential equation is our heat equation. The boundary conditions are given, there's two ways of writing it, but I would use this one. dt dx at x equal to 0 is equal to 0. Flat. It's symmetrical about the center line. And then right here, this one, t at L is equal to Ts. All right. So determine the temperature profile in the wall. Set up your differential equation, two boundary conditions, then mathematically solve to get the temperature profile. What's our differential equation? Well, it was a second derivative of temperature with respect to space. It was divided by Q dot over K, and then that's equal to 1 over alpha, the rate of change of temperature with respect to time. So we have three terms. This is conduction, heat source, and accumulation depletion. One of those three terms is 0. Which of those three terms is equal to 0 and why? Well, do we have a transient problem? There's nothing in this problem that says it's transient. Everything says it's steady state. Well, it never does say explicitly it's steady state. Well, then assume it's steady state because you can't do anything without making that assumption. So if it's steady state, boom, that's 0. So our differential equation looks something like second derivative with respect to x is equal to negative q dot divided by k. All right. And our two boundary conditions, I'm not going to repeat them. I'm going to just say this is boundary condition number 1, and this is boundary condition number 2. So there's our differential equation with two boundary conditions. What is a procedure from EA1 to solve this problem? Separate, integrate. You know, I would say that a few years ago, and people would just stare at me like, I don't know what you're talking about. And then I started harping on it. I was like, oh, please, just tell me separate and integrate, even if you don't know what it means or how to do it. And then now it seems like people know me. And they say, hey, if Monteufel asks a question, just say, don't say Leibniz rule. That's not going to work. Don't say, Newton-Raphson. Just say separate, integrate. He'll smile and say you're intelligent, and then everybody will move on. So let's go ahead and review separate, integrate, right? This derivative is the derivative with respect to x of the derivative of temperature with respect to x. Isn't that true? So when you separate, you're basically taking that equation and you're leaving dt of that, q dot divided by k dx. What did we do? What do you mean? I took this one and threw it over there and separated it. All right? Now I do the integration. When I do the integration, this side on the left is trivial. You just get back dt dx. You get back right here, minus q dot over k times x and the constant of integration. Now at this point, because we have a boundary condition number 1, in terms of a derivative, we can get that constant determined. So we would use boundary condition number one, and it will allow us to deduce something about c, this constant c. What is it? Well, you just look. It's this derivative is 0 at x equal to 0. Those two terms are 0. C has to be 0. So that helps. Otherwise, you got to introduce C1 and C2 and keep track and go, and then finally do your boundary conditions. But let's go here. I'm going to clean this up a little bit. Maybe I'm going to do this. Whoops. I'm going to clean this up a little bit too. Forget it. I'll just rewrite those. Minus L, 0, and plus L. Okay, now I have a little extra room. All right, so we do the separate again. So it's basically dt is equal to minus q dot over k times x times dx. I separate it. I integrate. I get t is equal to minus q dot over k 1/2 x squared plus a different constant of integration. But here now we use the boundary condition number 2, and there you look and you're saying that it's equal to ts at minus q dot over k 1/2 L squared. I put x equal to L, and this allows me to get what C is. So you can see C is equal to TS plus blah, 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 blah. Okay, then we put C back into the equation, and we get our final answer that in general, T is equal to TS plus Q dot L squared divided by 2K. I'm cleaning it up a little bit. 1 minus X over L squared. That's the answer that we were asked to solve for. That is our temperature profile in the wall. It looks quadratic. It's concave down. It's got a maximum at the center line, x equal to 0. Yes, there were a little bit of algebra right here, but I think you can handle it, right? Does that look good? Once you get the temperature profile, the next part B is going to be, give me the max temperature. Part C, give me a heat flux. Right? So let's go ahead and do that. Where is the maximum temperature in the wall? At x equals 0. You know, when I first came out of calculus, if somebody gave me a function f of x and they say, tell me what the maximum is, I would say, first of all, I need to find out where the maximum is, and then I can evaluate the function at that maximum. So I'd say df dx is equal to 0, and then I would solve to find that special x, and then finally stuff that back in, and then get the f max. But in heat transfer, don't forget what you're doing. It's not just pure math. You can say, guess what? The maximum's at x equal to 0. You can skip this hard step of trying to figure out where the maximum is. You know it's at x equal to 0, so just plug it into our temperature profile. And so temperature at 0 is equal to the maximum, which is equal to the surface temperature plus, what was it, Q dot L squared divided by 2K? I mean, make a little statement on the exam saying the maximum is at the location x equal to 0 and move on. All right. What is the heat flux at the wall? Well, this is the wall. What is the heat flux? You can do it two ways. You can do it conservation of energy, or you can go ahead and say, I have the temperature distribution. I'll use Fourier's law. Let's do it that way. So if you use Fourier's law, Q double prime at L, that's what we're asked to solve for, is minus k dt dx at L. Isn't that Fourier's law? I just have to get dt dx. Actually, from the previous slide, what was dt dx?
0.
That's the function as a function of x. And when I put in x equal to 0, it's 0. But I'm putting in x equal to L now because I need it at the wall. So it's negative q dot L over k. So this is negative q dot L over k. This is negative k, a little cancellation. And we pick up our final answer. The heat flux at the wall is q dot L. This is a summary of the solution for all those. Let's press forward to a new problem. We have a spherical problem. We have a given radius of 1.5 centimeter or 0.015 meter. We'll plug in numbers later. You have a heat generation rate given. The sphere has a given thermal conductivity, and it has a given surface temperature of 45 degrees C. First of all, get the temperature profile in the sphere. And so you start with the differential equation and boundary conditions. It's 1 over r squared, derivative with respect to r of r squared. I'm going to take that k outside, derivative t with respect to r, equal to minus q dot divided by k. That's where that k went. Does that look okay? Maybe you make a little sketch and say, okay, as a function of r, this is going to be my temperature. This is my cap r. It goes from 0 to cap r. And the temperature profile is probably going to be something like that. Isn't it going to be flat right there? Isn't one of my boundary conditions the rate of change of temperature with respect to r at 0 equal to 0? Yeah. And then the other boundary condition, temperature at cap r is equal to Ts. Well-formed mathematical problem. And now it's very similar to what we just did. What are you going to do? What's the strategy for solving this differential equation with two boundary conditions? Separate and integrate. And so if we separate, this equation looks like derivative r squared dt dr equal to minus q dot over k times r squared dr. There's the separation. And then we do the integration. We get r squared dt dr equal to minus q dot divided by k 1/3 r cubed plus a constant of integration. At this point, I would like to apply one of my boundary conditions. So we'll apply boundary condition number 1. We'll call this boundary condition number 1. And when we do that, it's like 0 times 0 is equal to a bunch of stuff times 0 cubed plus c. C has to be 0. That's the bottom line. Good. We're done with c, or that constant of integration. Now we clean it up and get back to our equation. Our equation now is going to be derivative of temperature with respect to r equal to minus q dot divided by 3k. And now I'm going to divide through by that r squared, so it's back just to r right there. You see that? A little tricky. Now we'll separate. dt is equal to minus q dot divided by 3k r dr. Now we integrate. T is equal to minus q dot, and here is 3 times 2 is 6k r squared plus another constant. I'm not going to work with C1, C2. It's just a new constant of integration. Now we apply boundary condition number 2 right here. And we get that Ts is equal to minus q dot cap r squared 6k plus that constant. So the constant, if you wanted to, I'm going to clean it up like, well, I'll write it like this. Constant's equal to Ts plus q dot r squared divided by 6k. Then our solution is going to be the temperature as a function of lowercase r is the surface temperature plus q dot r squared divided by 6k 1 minus lowercase r over cap r. It's quadratic, just like we had for the plane problem. So that's our solution for the temperature profile in the sphere. Where's the maximum at? Center. And so T max is at T at R equal to 0. So T max is simply Ts plus Q dot R squared divided by 6K. Solve for part B. And what is the heat flux at the outer surface of the sphere? Use Fourier's law. Q double prime is equal to minus K, derivative of temperature with respect to R evaluated at cap R. What we can do is we can come back to this one right here. And we can use it such that we get Q double prime is equal to minus K times minus Q dot cap R divided by 3K. The minus signs cancel, the K's cancel, and you're left with the Q double prime at the outer surface, cap R, is equal to Q dot cap R divided by 3. This is very, very similar, the whole approach, to the previous problem. We're almost done. I have a question for you, but let me show you this first. So this was the same equation. If you put in the numeric values for the heat flux at the outer surface, it's 140,000 watts per meter squared. If you get the maximum temperature in the middle, it's 59 degrees C for these values. And the surface temperature was 45 degrees C, right? Okay. If you can, make sure and write this value, this value, this value, whatever down. Because I think I continue this problem, and this is where I'm going to end the lecture with a little work it out on your own. So now we have our sphere, and we have fluid. And the fluid has a temperature of 25 degrees C. And there is convection from the outer surface. And what did we say that outer surface of the temperature of the surface was? Wasn't it 45 degrees C? Yeah. And the question is given the information, can you, part D, calculate the convection coefficient H? So at this point, what I'm going to do, I'm going to stop the lecture recording and that, and then I'll just check your results. And once you have that result, goodbye for today. Make sense?